Here in this video, we're going to look at how to find the average value of a function over an interval. And so if we have a function that is integrable on a closed interval from a to b, and we can determine the average value of that function. Now, by average value, we're talking about the average output. The average output, or value, is going to equal 1 over b minus a, which basically stands for the width of the interval. All right, so 1 divided by the width of that interval times the area underneath the curve, which is the definite integral from a to b for f of x dx. And so we're going to open up a Desmos window here, and we're trying to get a little bit more of a geometric idea of what the average value means. Okay, so looking at here in Desmos, we have the graph of some function, and it's shaded here below it, and that represents the area up underneath that curve along the x-axis from 0 to 5. And on the left-hand side, we have that the area up underneath that curve is the definite integral from a to b, which a is 0, b is 5, for this function, whatever it may be, and it tells us that the area up underneath the curve is 11.943. Well, the average value of this function is going to be equal to the area up underneath the curve divided by the total amount of space that elapses along the x-axis for the interval. So if I took the 11.943, divided that by b minus a, which is 5 minus 0, we would get the average value. The average value here in Desmos is represented by x, so I have the definite integral divided by the amount of space, and we get the average value of 2.388. And so that represents the average value. Now, so I'm going to make a representative rectangle here of the average value and what it represents. So geometrically, what we have is we have this rectangle in purple. The area of this rectangle in purple is equal to the area up underneath the curve. For instance, if I would take the 5 for the base and then the height that function is, which that height of that function is 2.389, and multiply those together, that is going to equal the same value for the area up underneath the curve. So the average value in context of a geometric figure is where the area up underneath the curve over an entire interval is equal to, we'd have the area of this average value rectangle, which represents the height of this rectangle is the average value. Okay, so mean value theorem for definite integrals. Basically, the mean value theorem for integrals says that the area underneath the curve between a and b, there will be some number c between a and b whose function value will equal the area up underneath the curve. So let's go back to Desmos here. So the average value, remember, the area up underneath the curve there is blue. And we determined that the average value, so if I took the area up underneath the curve, divided it by the width, we could create this rectangle where I have that height that represents the average value of 2.389. The mean value theorem for integrals guarantees that there will be some number between 0 and 5 where that function that we found the average value of will have that y value, which in this case, that x value along the curve that has that y value is 2.319. So that is the value guaranteed by the mean value theorem for integrals. All right, so let's go back and let's look at this picture here, and we'll kind of work our way through. So I want to write an expression that can be used to determine the area underneath the curve from a to b. Well, the area up underneath the curve is calculated by the definite integral from a to b for f of x dx. So whatever f is, the definite integral from a to b is going to give me the area up underneath that curve. Now, the area of the shaded rectangle, well, my shaded rectangle has a base of the distance from between a and b. So we'd say b minus a times, well, in this case, it's going to be the height of that rectangle is the function's value at x is equal to c, so times f of c. Now, this value, f of c, is the average value of the interval from a to b. So if that is the average value, if I look at my average value formula, the average value of a function is 1 over b minus a times the definite integral from a to b for f of x dx. All we did, if f of c is representing the average value, multiply the b minus a over, and we have the area of this rectangle here that we see on the right-hand side. The mean value theorem, coming back to it, the mean value theorem just guarantees that if f is continuous on that closed interval from a to b, that there will be some x value where the average value is going to equal the function value. So let's look at this first example. We want to find the average value of the function on the interval from 0 to 1, and we're given y is equal to 3x, or negative 3x squared minus 1. So the average value, our formula, so the average value would equal 1 over b minus a. Well, a is the first number in the interval, b is the second, so I'd have 1 over 1 times the definite integral from 0 to 1 for my function I want to find the area up underneath the curve of, negative 3x squared minus 1 dx. And then we would go get that value. So we wind up getting an average value of negative 2, and so we want to find the value c guaranteed by the mean value theorem. So that average value, if it was actually possible to add up every single one of the y values that curve produced from 0 to 1 and then divide by how many, we would get negative 2. So we want to figure out now the value c guaranteed by the mean value theorem. Where does the function equal negative 2 at? So I'm going to set my equation equal to negative 2, and I'm going to go solve for x. And we do that, we wind up getting 1/3 is equal to x squared. You take the square root of both sides, and you're going to get 1 over the square root of 3 is equal to the absolute value of x. Now we have two possible cases for this. We have x could equal the positive 1 over the square root of 3, and we have x could equal negative 1 over the square root of 3. The mean value theorem will only guarantee the number that falls inside of that interval from 0 to 1, so the value guaranteed by the mean value theorem is 1 over the square root of 3. All right, so now we're going to graph, so we see that the area up underneath the curve is negative 2. The average value just happened to be negative 2 as well. Mean value theorem guarantees somewhere between 0 and 1 that the function that we're finding the area up underneath the curve of will equal that average value somewhere. And so I graph it, and so I graph that line and see where they intersect. They intersect at 0.577, which is equivalent to 1 divided by the square root of 3. All right, let's look at this next example here. All right, so position of a particle moving along a line is given by the function, and I forgot a letter here, let's say s of t, is equal to negative t to the third plus 6t squared minus 2. Find the change in position from time is equal to 0 to time is equal to 2. Well, that's the same thing as my displacement. So displacement, I would take my position at 2 and subtract my position at 0, and that would be my overall displacement from start to finish. Well, if I put in 2 for s, I get 14. If I put in 0 for s, I get negative 2. So 14 minus negative 2, my overall displacement is 16 units. Now, depending on what direction we were moving, if we're moving left or right or up or down, since my displacement is positive, I would either be located to the right of where I initially was, or I'd be located above where I initially was. Okay, second one here, find an equation for the velocity, and then find the velocity when time is equal to 2. Well, velocity is equal to the derivative of my position function, so my velocity equation here would be negative 3t squared plus 12t, and then the derivative of 2 is 0. And we would just find that value when we put 2 in. And so negative 3 times 2 squared plus 12 times 2. And we wind up getting a velocity of 12 units. Next, we want to find the acceleration. Well, acceleration is the second derivative of my position function, or the same thing as the derivative of my velocity equation. So I'm going to take the derivative again right here. We'd end up with negative 6t plus 12. And we want to find the acceleration when time is equal to 2, so I put in 2 for t, and we're going to wind up getting, so negative 6 times 2 plus 12, which gives us 0, so the acceleration is 0. All right, next we'll find the average rate of change of the position function, which is also known as the average velocity of the particle, from 0 to 2. Well, the average rate of change of my position function would be s of 2 minus s of 0. So my overall displacement divided by the change in my time. And so s of 2 minus s of 0 over 2 minus 0. Well, the displacement over that time interval we found to be 16. Divide that by 2. The average rate of change of my position function is equal to 8. So next what we want to do is we want to integrate the velocity function over the interval from 0 to 2. All right, so if I integrate my velocity function, so from 0 to 2, our velocity equation, negative 3t squared plus 12t dt, and we evaluate that, we wind up getting that to equal 16. Now, what do we notice in terms of, look at our other answer, see where else we equal 16 at. So we got 16 when we did this. We get 16 right over there in that problem. And so what we can do is we can relate those two together and say, well, wait a minute. So when I found the value of the definite integral of my velocity equation from 0 to 2, that ended up being my displacement, s of 2 minus s of 0. Okay, well that's going to be interesting for when we get into another part. Now let's use our calculator to find the average value of the velocity function over the interval from 0 to 2. So the average value formula for velocity would be 1 over b minus a, so 1 over 2 minus 0, times the definite integral of what we're trying to find the average value of. So the average value of my velocity, v of t dt, is going to equal, well, we've already integrated our velocity function, and we got 16, so it would be 1/2 times 16. And so we get the average value to equal 8 here. Now let's see where else we see that value at. We have a value here of what we just did of 8. We also see that over here at the average rate of change, which is interesting to us because what that means was the average rate of change of our function, s of 2 minus s of 0, over 2 minus 0 is equal to the average value, so 1 over 2 minus 0, times the definite integral from 0 to 2 of v of t dt.